At any point that you need to stop the video and finish writing something down, you can just press the pause button. So after we've talked about complex numbers and imaginary numbers, the next thing we're going to talk about is how to organize them. So in the very beginning of the year, we talked about irrational, rational numbers, integers, natural numbers, whole numbers, and complex, or we talked about these. So the only thing that we're going to add to our Venn diagram is the complex and pure imaginary numbers. So we're adding to our diagram that we had at the beginning of the year. So first of all, we have complex numbers. And that consists of everything. Then, after complex numbers, we have the imaginary numbers and the real numbers. So the pure imaginary numbers go here. And they're still represented as I. And then our real numbers go here, represented as the big R. Now the rest of these should be reviewed. After we have real numbers, we have the irrational, which is represented by the big I. So some of y'all asked, why did we use little I? And that's because if you had the big I, it means irrational. So you need to make sure you keep the two separate. And then we have the rational. And I misspelled that. Numbers. After rational, you have integers. Which is represented by the Z. Whole numbers. And then natural numbers. So in order to classify these, first we have to make sure that our numbers are simplified to its basic form. So we have to simplify it. So remember, if I have the square root of a negative number, I first have to separate it into the square root of -1 times the square root of 64. And once you can figure out that, if you remember, the square root of a -1 is I times the square root of 64, which is 8, so my answer is going to be 8i. That is the simplified form. Now, the second step of the instruction says to name all the sets to which each value belongs to. So if you go back to your diagram, well, if you notice, all numbers are complex, whether they're real or imaginary. So they're all complex. So I know I can write a C. Now I have to ask myself, is it a real number or imaginary? Well, I have an I, so that means it's imaginary. So this is my answer. Number 2. 10i times -2i. Okay, I have to multiply my numbers together. 10 times -2 gives me -20. And then multiply the i's together. I times I gives me I squared. Now, if we remember the diagram, with the 4 i's, and you remember what I say, and if you choose to use something else, great. But the way I do mine is I1, I1, positive, negative, negative, positive. So I squared is negative 1. So I'm going to do negative 20 times negative 1, which gives me positive 20. So positive 20 is a complex number. It's real. It is rational because it doesn't have a decimal. It is an integer. There again, because it doesn't have a decimal. It's a whole number because it's not negative. And it's a natural number because it's bigger than 0. So remember, natural is 1, 2, 3, so forth. Whole is 0, 1, 2, 3. Integers is negative 2, negative 1, 0, 1, and so forth. Rational is all of the above, including, so it's a natural number, it's a whole number, it's an integer, including fractions / ending decimals. And the irrational are your never ending decimals. That was just a quick review because we've already covered those. So if you look at number 3, you can rewrite number 3 as the square root of 1 over the square root of 9. Well, the square root of 1 is 1, and the square root of 9 is 3. So that is simplified. So now I just have to name all the sets of numbers that it entails. Okay? So if you go back and look at your list, you can say, well, it is complex. It doesn't have any imaginary numbers in it, so it's real. It's a fraction, so it's not irrational, so it's rational. But it's not an integer because it is a fraction. So it's just these. Okay, so this is just a review over how to organize real and complex numbers. So I'm going to stop right here, and I'm going to tell you to try to complete 4, 5, and 6 on your own. You should already know how to do these from Thursday of last week and working a little bit yesterday. So if you have any questions, please raise your hand and I'll come around and help you. Okay, so I'm going to skip down to number 7. Anytime I have just a one term inside a set of parentheses, I can rewrite it, if you like to rewrite it, as negative 2 cubed times I cubed. Okay, so negative 2 cubed is going to give me negative 8 times I to the third, which is, if I look back up at my list, negative I. So it's going to be negative 8 times negative I. Well, I know that a negative times a negative is going to give me a positive 8I. So let's look at the second part. That's just the first part. If I rewrite it, like I said, as I squared times the square root of 7 squared. Remember, a square and a square root cancels each other out. So what I'm left with is I squared times 7. But we know what I squared is. I squared is equal to negative 1 times 7, which gives me negative 7. So all I have to do now is multiply 8 times negative 7, which gives me negative 56i. So when I know it's a complex number, and because it has I, it's imaginary. That's my final answer. I'm going to work with number 8 now, because some of you are still kind of struggling with the full method. Okay? So I'm going to do the full method. 3 times 3 is 9. 3 times 5 is positive 15i. Negative 5i times 3 is negative 15i. And negative 5i times positive 5i gives me negative 25i squared. So combine your like terms. Those are my like terms. So positive 15i minus 15i just cancels out. So I'm going to be left with 9 minus 25i squared. But we know that I squared equals negative 1. So it's going to be 9 minus 25 times negative 1. Well, negative 25 times negative 1 gives me a positive 25. So I'm going to move up here. So it's going to be 9 plus 25. So when I add those together, I get 34. Because 34 is complex, you ask yourself, is it real or imaginary? Well, it's real. Doesn't have any eyes. So is it irrational or rational? Rational. Is it an integer? Yes. Is it whole? Yes. Is it natural? Yes. So that's my answer to number 8. Number 9. If you remember correctly, when you have I to a big number, I showed you the way that I always remember how to do these. So I'm just going to rewrite my I's out. It's I1, positive, negative, negative, positive. So when you divide this number, the 16, by 4, if you get 0.25, you use I. If you get 0.5 as the ending decimal, you use negative 1. 0.75, you use 3. And if you get a whole number, you use I to the 4th. So when I do 16 divided by 4, I get 4, which is a whole number. So I'm going to say that I to the 16th equals positive 1. Now, when I go to name all the sets in which the value belongs, I'm going to use positive 1. So positive 1 is a complex number. It's real. It's rational. It's an integer. It's whole. And it's natural. Number 10. Square root of 50. Remember, I have to find the biggest perfect square that will go into 150 because 150 is not a perfect square. So I have to split it up. The biggest perfect square that I found that went into 150 was 25. So the square root of 25, what times 25 will give me 150? Well, if you use the calculator and you do 150 divided by 25, you're going to get 6. So over here should be the square root of 6. So the square root of 25 is 5. And the square root of 6 doesn't simplify, so it stays the square root of 6. So to name all the sets to which this number belongs to, well, I know it's a complex number. Because there's no i's, it's real. And because it has a square root, it is irrational. Almost wrote the wrong letter. It is irrational. So go to the next page. Properties of complex numbers. So we talked about how to organize the numbers and to classify them. So the next thing we need to talk about are the properties. The properties of real numbers are commutative, associative, identity, inverse, and distributive. And they can also be applied to complex numbers. So for questions 11 and 15, write an example of the property using the complex numbers. Well, the commutative property of addition is something that looks like this. If I have 3 plus 2, it equals 2 plus 3. So I just change the way that it's written. So if I want to use a complex number, you can say, okay, 3 plus 4i equals 4i plus 3. The associative property of multiplication basically says that if I have 2 times 3 times 4, remember, when I use an order of operations, I have to do what's inside the parentheses first. So if I do 2 times 3 times 4, it'll equal the same as 2 times 3 times 4. So if I use an example using complex numbers, I could say, okay, 2 times, I'm going to use a bracket because I'm going to use a parenthesis in a second. 3 times 4 plus 5i it will equal the same as 2 times 3 times 4 plus 5i. The distributive property looks something like this. Where when I distribute within the parentheses, it'll come out to be 6 plus 10. So if I use an example of complex numbers, I'm going to use 5 times 6 minus 7i equals 30 minus 35i. Okay, the identity property of multiplication just wants to know what do I have to multiply by to get the exact same thing. So if I have 3, what do I have to multiply it by to give me 3? Well, 1. So if I had 7i, what do I have to multiply by to give me 7i? Same thing, 1. That's the identity property. The inverse property of addition wants to know what do I have to add to it to give me 0. So what do I have to add to 3 to give me 0? Well, negative 3. So what do I have to add to 3 minus 8i to give me 0? Well, to cancel out a 3, I have to have negative 3. And to cancel out a negative 8i, I have to have a positive 8i. So all I did was change the signs. So let's look at some examples. For each question, 16 through 21, name the property that justifies the statement. So 16, I had 2i on the outside, and it looks like they did 2i times 7, well, 2i times 7, and 2i times 5i, negative 5i, well, distributive property. On 18, it looks like I'm adding this first, but over here I'm adding this first. So I'm just changing the order of my parentheses. Well, if I look back up here, changing the order of the parentheses was number 12. The associative property of multiplication. Where'd you fly? I'm sorry, not multiplication, because we're not multiplying, we're adding. And I don't know why my smartboard is messing up. So the associative property of addition. Number 20 is if you look at number 20, it almost looks like it's going to be the same thing as number 18, but there's a little difference, okay? Let's look back at 18 real quick. If you notice, I have negative 5i plus 4i plus 9. And then I have negative 5i plus 4i plus 9. So the order of the numbers never changed. So if the order of the numbers don't change, then it's associative. If you look at number 20, it says negative 6i times 2i times 8. And then it says 8i times negative 6i times 2i. The order changed. That is the commutative property. of multiplication because we're multiplying. Okay, I'm going to let y'all try 17, 19, and 21. And there again, if you have any questions, please let me know by raising your hand. Number 22, name the additive and multiplicative identity of 6i. So I have to name two things. So we're looking at the identity property. So the identity property is number 14, which says I want to get the exact same thing as I started off with. So the additive property. If I start off with 6i, what do I add to 6i to give me 6i? 0. With the multiplication property, you ask yourself, what do I multiply 6i by to give me 6i? 1. Number 23 says name the additive and multiplicative inverse of negative 8 minus 3i. So if I look back at the top, the inverse property says what do I want to multiply or add by to get to 0. But that's the thing. With addition, it's to get to 0. With multiplication, it's to actually get to 1. So depending on which one you're doing, it's either 0 or 1. So if I'm going to do the additive one, and I have negative 8 minus 3i, what do I add to it to get to 0? Well, to get negative 8 to 0, I add 8. To get negative 3i to 0, I add 3i. With the multiplication, what do I multiply by to get to 1? Well, when I have a whole number like this, all I have to multiply by is the reciprocal, which means you just flip it. So pretend this is over 1 and just flip the fraction. So I'll multiply by 1 over negative 8 minus 3i. (24 through 28). For these questions, you're going to answer true or false. If false, provide a counter example. Okay? 24. The set of complex numbers is closed under addition. Which means, when you ask yourself these, I'm going to go back to this page. Okay? It says the set of complex numbers is closed under addition. So if I have a complex number and I add it with a complex number, do I still get a complex number? So, for example, a complex number is 3 plus 2i plus 4 plus I. Just random. Okay? So if I add all this together, because I have two complex numbers here, here and here, 3 plus 4 is 7. 4i plus I is 3i. Well, that's still a complex number, So it's true. $25. The set of complex numbers is closed under division. Well, if I have 4i divided by I, remember, get rid of the I in the bottom, multiply both sides by I, so that it get 4i squared over I squared, which gives me negative 4 over negative 1, which gives me positive 4. Well, 4 is still a complex number. So this one is also true. All complex numbers are pure imaginary numbers. This one is false. Because if I look back at my chart on the previous page, it's saying all complex numbers. So it's saying all of this is also pure imaginary. Well, that's false, because if I have a real number is complex, but it's not imaginary. So you could use 3 as an example. 3 is a complex number, but it's not an imaginary number. Or you could use 7 plus 2i. 7 plus 2i is a complex number, but it's not a pure imaginary number because it's connected to a real number. $27. A number cannot be both irrational and complex.
Ms. Mitchell, Dr. Rayburn, please.
Number 27 is also false, because you can have an irrational number that is also complex. For example, the square root of negative 47 plus 3. That's irrational and complex, because it equals, I should get rid of this comma and put equals, because it equals 3 plus I square root of 47. 28. The product of a real number and a complex number is a real number. This is also false. Here's why. I'm going to do 2 times 3 plus 2i. Okay? So the product meaning multiply. So I'm multiplying right here. Of a real number. 2 is a real number. And a complex number. This being the complex part. Is going to give me 2 times 3, which is 6. 2 times 2 is 4i. So it's still a complex number, but it's imaginary because of the I. So here's what I want you to do. On a separate sheet of paper, I want you to answer the problems that we skipped. So 17, 19, and 21 on a separate sheet of paper, and 4, 5, and 6. I also want you to go through and come up with an example of your own for 11, 12, 13, 14, and 15. So I want you to come up with an example other than the ones I've already used of each of these properties. So come up with your own example. I think that was it. So I'm going to just re-say what I want you to do now. Come up with your own example of these. 11 through 15. Answer 17, 19, and 21. And on the next previous page, answers 4, 5, and 6. All on a separate sheet of paper. Due at the end of class.